So, welcome back. So now we'll talk about the Canadian Total Diet Study with Dr. Robert Dabeka. He's obtained a PhD from the University of Regina in 1975. Then he worked for 2 years at the analytical section of the National Research Council of Canada. He has been working as a research scientist at Health Canada in the Food Research Division for 46 years, and as a project leader is mainly responsible for the analysis and surveillance of toxic trace elements in food and for the Canadian Total Diet Study. So, Robert.
Thanks, Veronique. Can you hear me? Okay. Thank you very much to my thanks to BFR for the invitation to give this presentation. And may as well start. In Canada, food safety is divided, at the federal level, is divided into two organizations, the Canadian Food Inspection Agency. They enforce the food safety regulations, and as well they conduct food monitoring. Food Directorate sets food safety policies and conducts research, risk assessments, sets regulations, guidelines, recommends risk management measures. The Total Diet Study runs from within the Food Directorate. The bureau that I work in is involved with the safety of potentially toxic chemicals, and it has 3 divisions. Food Research Division, we do the analytical method development and conduct many surveys to assess human dietary exposure to chemicals. And we run the Canadian Total Diet Study. Regulatory Toxicology Research Division, they do animal studies, conducting toxicological research on the safety of chemicals with animals. And our Chemical Health Hazard Assessment Division, they do our risk assessments and recommend and develop regulations and guidelines. Now, everybody knows about the objectives of total diet studies. Number 1, get representative background concentrations of priority chemicals in prepared foods, estimate the dietary intake of priority chemicals by average Canadians in different age sex groups, and if you can, identify unexpected contamination and time trends of dietary intakes and chemical concentrations in primary foods. This is Canada. The cities, there are 10 cities where we conduct regular sampling. They're all located in the southern half of the country. In terms of our size, we're about we have half the population of Germany. We're at 38 million. Our area is 9.98 million square kilometers. That's about 27 times the area of Germany. And from east to west, we have 5,500 kilometers. And that's about the same distance as our 2 distant sampling cities. So the logistics here of collecting samples and bringing them into we cook everything in Ottawa, which is somewhere southeast of the center of Canada, but we have to get the food samples in, and that's generally done by a Purolator. Our Canadian Food Inspection Agency, inspectors, they pick up the samples, we provide them with actual training. One of our cooks goes down, trains them how to package and shop, and they pick up the samples, document them, and ship them by Purolator to Ottawa. Continuing, 22% of the population are immigrants from over 140 different countries, so we're dealing with a lot of different languages as well as culinary preparations for the same small number of foods, but we're actually increasing the number of foods because of imports. 5% of the population are indigenous, 18% are rural. Canada imports food from about 160 different countries. What surprised me, I found this: 75% of fresh vegetables eaten in Canada are imported, which just astounds me. Like we could probably grow a lot more of these things ourselves. Well, back to our objectives. Background concentrations, dietary intakes, and looking for contamination sources. And let's look at this, our sampling procedure. We sample one of the 10 cities once a year over a 7-week period. That means we don't have representation which is seasonal or regional, and we're limited to a 7-week period of the year. We pick up 244 different foods, and each is picked up as 4 brands, different brands. Usually the inspectors go to 4 different stores to pick these up, or 4 restaurants if it's a restaurant food. And this definitely isn't statistical, but we'll see if it works. We end up with 159 food composites for analysis. This is stretching it a bit, but it's comfortable for one research scientist supported by one or several technicians to analyze every year and still do other work on the side. And the problem is we analyze our food composites using high sensitivity methods. Here's a list of some of the chemicals: the pesticides, PCBs, dioxins, PBDEs, and trace elements have been analyzed every year on a long-term basis. The pesticides, the first 3 have been shifted because of analytical resources. We do those once every 2 years now. Trace elements we still do every year. In addition, we have a new scientist who's been with us for a while, but he's been active in analyzing the trace elements for phthalates, DEHP, bisphenols, volatile organics. And probably about 10 or 15 years ago, I approached our Radiation Protection Bureau, and they've been doing our radionuclides and the total diet study ever since. 3 scientists, including Stephen Kaiser from Radiation Protection Bureau. 3 of them in our own division are involved with the majority of all the analysis we produce. The objective of our analysis is to achieve sufficiently low limits of detection to actually measure the background concentrations of the chemicals in the foods. And characteristics: expensive, sensitive instrumentation, high complexity, you need pre-concentration separation steps, contamination control, and high analytical expertise. And the rationale for all this is you can't identify a contaminated sample if you don't know the chemical concentration of an uncontaminated one. And finally, the other rationale is to improve accuracy of dietary intake estimations. Here's an example of the low levels of lead we're achieving in our total diet samples. Probably 20 or 30 years ago, people had difficulty getting down to 10 ppb in terms of detection limits. We're down to about 0.1 or 0.2 ppb for the milk. And you can see the actual analytical results of duplicates and the RSTs we're getting for the duplicates of the composites. And finally, estimating the dietary intake of priority chemicals by average Canadians. We do deterministic calculations. We average concentration Basically, I think all of you know about this, but we have 16 H6 groups based on 1970 to 72 survey data. Data are old and available for only 127 composites, but the data are currently being updated. Again, we conduct deterministic composites, which take the concentration multiplied by the amount eaten and to add these up over all composites to give the dietary intake by the H6 group. Now, I've noticed over the years when people used our data, they forget this thing about you have to deal with the individual composite intakes of the individual composites. And they try to average all our analytical results for vegetables and take all the total dietary intake of all the vegetables, and they think they're getting the right result or not. You have to do it on an individual basis. These are our age-sex groups, and I'm pleased to see that, for example, the French TDS, I believe German as well, they're getting down to infant dietary intakes. These original data that we have, they break it down even further, and we can get down to 0 to 1 month, 2 to 3, 4 to 6, 7 to 9, and 10 to 12. What worries me is I've seen dietary intake start at 6 months of age, and it really doesn't, it doesn't, doing this you miss out on actual life. I think the rationale for some of it is you're supposed to be breastfeeding or formula feeding for the 6 months with no food, but in reality parents give their children food, even in these young age groups. Here's the impact of detection limit on the dietary intake for a single composite. If you use 10, you'd get 1,000 nanograms intake. If you used 100 nanograms. And if you've got an actual concentration of 0.3, then it should be 30 nanograms. What is being done right now is if you can't detect something, you either use the limit of quantitation or limit of detection and calculate using those values, or and that will give you an upper bound limit, or you replace the less thans with zeros, and that gives you a lower bound dietary intake. Here's the actual effect of the dietary intake, substituting in a real data set the for lead data. Instead of 0 for less thans, we can get one value if you use 0.1, 0.2, where our detection limit is. We're slightly higher. As soon as you get to a detection limit about 0.3 nanograms per gram, that's equivalent to a quantitation level of 10 nanograms per gram, but you're increasing the parent dietary intake by about threefold. Now, ability to identify unexpected contamination in foods. Again, I'll repeat, we only sample 4 brands of each food. And we do this because if one of the brands happens to be contaminated, we will see it. We do time trends for each composite, and but again, one city, 4 brands, 7 weeks a year is can you do a times trend, and you can do it for concentrations and for dietary intakes. I should mention that a portion of the dietary TDS composites that are prepared each year I think it's 4 bottles, two bottled in glass and 2 bottled in plastic, are archived. And these samples go back in time for, I'd say, close to 20 years now. Gradually, some of our new scientists coming on will want to study one or another chemical, when it appeared or if it's present from a long time ago, but they take our TDS samples and they can use them. Here's where you can find our results posted. I'm sure the presentation will be available to you afterwards. Interpretation of our results: tap water from the target city and kitchen preparation area are collected and analyzed, but only the water from our kitchen preparation area in Ottawa is used to prepare the samples. Tap water consumed as tap water directly is not included in our dietary intake calculations. Foods prepared in the lab are not seasoned or salted. And to improve the statistical power of some chemicals, we can average dietary intakes over several cities or years and get a better estimate of what's happening with time, or just to get a better estimate of accuracy across the country. Some results: chloropyrifos organophosphate. This is looking at years between 2003, 2005, 2013, and 2015. Only one sample of celery came out high for that period. That was in 2013. Toluene in selected TDS samples. What's interesting is I was planning on in our next rework of the total diet study, I was thinking of combining white and whole wheat bread into one composite. And so I've changed my mind after seeing this data because the whole wheat bread is much higher in toluene than in white bread. That means something's going on. And the crackers are higher still, so sometimes it's fortuitous that you pick out some of these things. DEHP, that's a phthalate in selected vegetable samples. Not much change for the different vegetables, or canned or non-canned or anything. But they're present there. Now, this is an interesting one, BPS. It's been created as a substitute for BPA because of toxicity of BPA. But from what I've heard, that BPS toxicity is approaching that of BPA. But we're finding variable levels, and this was done retrospectively for some of these years. Going back to 2008. And we're finding the BPS is present first because we haven't got a clue as when BPS was introduced into tin cans, into the epoxy in tin cans. And secondly, it's jumping around a lot. And when we look for BPS in beefsteak, that was hamburger meat. Beefsteak, they're generally much lower. There's a couple of high values there. And 2 weeks ago, we listened to a lecture from Stéphane Bayen. He works at McGill University. And he was using QTOF for analysis of chemicals in foods. And his postdoc there She picked up a sample of salmon. I believe it was salmon. I don't know if she mentioned the fish name. But it was sealed packaged, about this long, and it had a thermal paper sticker on it with the price, the weight, and that it was a fish, obviously, and it was stuck on the paper. She took it, bought it, took it to the lab, left it in the fridge for 5 days, which she shouldn't have done. But then what she did was she cut it in half carefully and analyzed one half. The paper was stuck on one half, so she separated the half which had the paper and from the other half, which didn't have the paper. And in the fish itself, on a whole weight basis, they found over 1 ppm BPA, and just a trace in the other half of the fish. So somehow they think that the BPA has migrated through the plastic, or stuck to the plastic, migrated through the plastic into the fish and contaminated it. But we haven't seen anything like that in our total diet study, but there's probably a reason for that, is that after we purchase the fresh meat or fish, we freeze it. The inspectors bring it to their lab, they freeze it, then they ship it frozen. So there isn't a time for that, for the transference of BPA, if there is BPA in BPS, if there is BPS in the level. So this might explain some of the things we're seeing. The variability the variability we're seeing from year to year. Here we have PBDEs, the sum of 17 congeners over a year, between the years 2003 and 2015. And it looks like, I guess 2007 looks highest for some reason. In almost all the samples except the pizza, but it really doesn't make it, I can't understand the reason why that would be the case. But anyway, it's present in a wide range of foods. It's a flame retardant. Dieldrin and meat products, we only found it at a moderately low level in 2003 and 2005 samples of hamburger. It was much lower in the other, from steak to pork to poultry, ground beef, etc. Here we see the sum of DDT congeners in TDS dairy products over time. And we're seeing a general decrease, and this is between 1998 and 2015. And here we see an increase in bismuth in cheese samples here, but we've seen it in milk as well. And what happened around 2002, farmers started injecting bismuth paste into the udders of cows at the end of their milking seasons. And when the cows would start giving milk again, when they started milking the cows, there was the idea was that this bismuth would be removed on the first batches of milk coming out, but traces still remain. And I guess the cheese industry people, they complained about this, and it was because for aged cheese, the bismuth was migrating together and creating black spots in the cheese. And lead, this is old data, and mid-80s, we detected lead in raisin pie in our total diet study. Our regional labs picked up on it, and they traced the lead. They conducted a mini survey of lead in raisins sold in Canada, and the Turkish raisins came out really high. Eventually, we stopped the importation of these raisins, and the pressure put on our director at the time because of this was astounding. If he didn't know the analysts, if he didn't know the analysts personally, he would have just passed the raisins, let them come into Canada. But they were saying they were threatening not to buy $2 billion worth of nuclear reactors and things like this. But the industry there and the import groups can be very powerful and influential. Now here's an example of all-age dietary lead intakes with time. And we see the effects here of the gradual transfer from lead soldered cans to lead-free cans. And between 2000 and 2009, there's city-to-city differences, but if you take an average of it and look at the variability, the relative standard deviation is about 15%. So even with the minimal amount of sampling we do, we can still get a reasonable, stable dietary intake result. We did some comparisons of deterministic and probabilistic, but I have to correct the deterministic values are wrong. And they come out fairly close to each other, but the interesting thing is this deterministic, we're still being done using 1970 to 72 consumption values and body weights. Whereas the probabilistic, we're using the current 2005 consumption values and body weights. So it's astounding that you can get such close values between the median and average. Conclusions, TDS chemical concentration data. With our TDS, we can get a fairly reliable representation of background concentrations and still identify contaminated samples and time trends. And our dietary intake data provide an accurate core data for risk assessments and can identify time trends and monitor impact of risk management steps. For the core data, I say core data here because we're using old consumption values, but they can still be used combined with current concentration data, and even be combined with current consumption values from our more recent surveys to do a more careful risk assessment. Hidden benefits, the archived samples, and the analysis of priority chemicals every year or 2 years ensures the availability of analytical expertise to deal with emergencies. We found that really important in the dioxin case incident, in that we had a laboratory analyst on staff, and within a month we had actual analytical results, which we could say that Canada wasn't, the food imported into Canada was not contaminated with dioxins. Future design factors, ethnic regional diets. I don't think we have the resources to deal with this. And even our Statistics Canada food consumption surveys are not including a lot of this information. The ethnic diets, they're breaking down into recipes primarily. And we can deal with that with our existing composites or modify them slightly. Mapping TDS to current 2015 food consumption data that's in progress. What we'd like to do is add drinking water consumed as water. The chemicals can contribute to the dietary intakes. And with our new consumption data, we'll be able to do that. And finally, the big problem is incorporating new composites to represent thousands of new products for sale and dietary changes, and balancing this with analytical resources. This has been mentioned with respect to other total diet studies, and the answer is to break the different preparation techniques down into recipes. Thank you very much.